Okay, so hi everyone. So yeah, so today so it's lecture 23, and so by the way, the midterm grades will be released this evening, and you'll receive details about regrades and so on. People did really well in the midterm. The median was 82, which is great. But anyway, you'll get more information about that on email. So today is the last lecture of the purely linear algebra part of the course. And let me just turn on the chat in case somebody is saying something. What I'm going to do today is I'm going to finish talking about singular value decomposition, and then I'm going to start talking about differential, which is what we're going to spend the last 3 weeks of the course on. And it's a really nice application of the concepts we've learned, as well as the important, right? So let me start by saying something about singular value decomposition. So what did we do last time? Well, last time we did the SVD, and what that is it's the following decomposition. So given any m by n matrix, you can consider the n by n matrix A transpose A, which is symmetric. And this, because it's symmetric by the spectral theorem, it has some real eigenvalues, k of which are non-zero, and some corresponding eigenvectors v1 through vk, and maybe it actually has a whole orthonormal basis of eigenvectors. And then we observed this sort of important observation that actually, if you look at these non-zero eigenvectors, the v1 through vk, they form a very special orthonormal basis for the row space. So you get that, well, these v1 through vk that you get in this way are an orthonormal basis for the row space. Okay. Further, if you now map these under A and normalize, you get some other vectors. So U1 equals A V1 divided by norm of A V1 all the way up to UK equals A VK divided by norm of A VK. This is an orthonormal basis for the column space of A. And so this is very special. This is not something that just happens for any old orthonormal basis. So these vectors are important. I mean, I guess I'll just mention the terminology. These are called the right singular vectors. And these are called the left singular vectors. And the relation between these vectors is, you can sum it up in this equation, that A Vi equals sigma I ui, where sigma I is this normalizing constant by definition, which also, if you go back to where these vectors and these numbers came from, this is just a square root of the ith eigenvalue lambda I of A transpose A. And these numbers are called the singular values. And the key equation relating the left-right singular vectors and the singular values is this, as well as the key properties that these are both orthonormal bases. This is what's special. So if you write this information in matrix notation, which we did at the end of the last lecture. Oh yeah, so somebody asked, are all the eigenvalues non-zero? Yes, all are non-negative, but the first k are strictly positive. So if you write this in matrix notation, which we did last time, we derived something that in the book referred to as the truncated singular value decomposition. And what that is if you just write the equation in the red box in matrix notation and use some facts about projections, you get this factorization that A is equal to U sigma V transpose, where U is, so A is M by N, U is now M by K. The columns of U are the UIs, and there are K of them. Sigma is K by K, that's a square matrix. And so sigma, I'll just write what everything is here. U has the U's, V has the V's, and sigma is just a diagonal matrix containing the positive singular values. So here, the K that's coming up here really is equal to the rank of A. Okay, so that's what's normally called the truncated SVD, and this V transpose is going to be K by N. This gives a way to write this additively using the grad school matrix multiplication formula as a sum of these rank 1 matrices UI VI transpose. But this is not quite as good as the spectral theorem. The UI VI transpose are not orthogonal projections because the U's and V's are not actually the same, right? So they're not literally a matrix of an orthogonal projection. But the VI's are orthogonal. So in that sense, when you multiply a vector X by V transpose, it is getting decomposed into components along an orthonormal basis for some subspace. So that's called the truncated SVD. And I should just mention that there's something called the full SVD, which is a slight modification of this. So what is the full SVD? Well, let's think about how we got the truncated SVD. We got it by writing this red box equation in matrix form, right? So we wrote it like AV1 through VK, leaving some space here, equals U1 through UK times this matrix that had sigma 1, sigma 2 up to sigma k. Okay, that's what happens if you write the equation in the red box, in matrix notation. Now, what the full SVD is that, well, these matrices U and V in the truncated SVD are rectangular. The full SVD is this alternate point of view that, well, why not make these square matrices by completing these orthonormal bases, right? So V1 through VK are already orthonormal, right? So these are, I'm sorry, this should be N. So what I can do now is I can actually just, right now this is an N by K matrix, but if I just add the rest of the eigenvectors, this will become an N by N matrix, right? So this is the first K eigenvectors. So this part of the matrix is N by K, and the second part is N by N minus K. So if you stick them together, you get N by N. Similarly, I can extend this orthonormal basis to a complete orthonormal basis of Rm. And I can do that by just by Gram-Schmidt, actually. Right? If I have an orthonormal basis for a subspace of Rm, and now I want to extend it to all of Rm, well, I just choose, well, I can choose some basis for the orthogonal complement and run Gram-Schmidt on that. And then I'll get an orthonormal basis for the whole thing. But now what happens to the equation? So I'm going to have to extend these matrices as well for this to make sense, right? So by the way, this is now, so this part is m by k, and this part is m minus k by k. So what's going to show up in the I'm going to have to extend the sigma matrix, right? Because this is m by n. So m by n times n by n has to equal m by m times, this thing better also be m by n, right? For this to make sense. But now what goes here? Well, just 0, right? Why? So why is there going to be a 0 all through here? Can anybody explain?
I will hypothesize that I'll probably hypothesize that, well, they're going, because I think I'm just wondering, is A going to be some, well, it's going to, I was thinking about some things that happens in a projection matrix, but I think it probably happens to be that those other vectors end up being the eigenvectors of 0, or?
Yeah, exactly. Not quite eigenvectors. The reason is, if you look at what this, if you just look at the, I mean, you have to think about, you know, let's say k plus first column of the matrix. What is this equation saying? It's just saying that a vk plus 1 is equal to 0 times uk plus 1, all the way down to a vn is equal to 0 times un. Okay, so these zeros are kind of meaningless. They just, I mean, not meaningless. They're kind of not relevant. They just correspond to the fact that A actually kills all the right singular vectors after okay. And then there are also going to be zeros here. You can just check that. So you basically just pad the thing with zeros to make it m by n.
They're not eigenvectors, since A is not a square matrix.
They're not eigenvectors. They're singular vectors. Exactly. They're not eigenvectors, right? The VIs are eigenvectors of A transpose A, but that's not the same thing as A. So okay, so when you do this, what you end up getting finally, when you combine this, is you get the same equation, A equals U sigma V transpose, but with different dimensions. This is now m by m. This is n by n. And this is m by n. Okay. Now, the thing you gain for this is that U and V are now actually orthogonal matrices in the full SVD. Whereas in the truncated SVD, U and V are not actually orthogonal. They just have the property that U transpose U equals identity and V transpose V equals identity. But they're not actually orthogonal, right? If you multiply them in the other direction, you get certain orthogonal projections. So that's the difference between full SVD and truncated SVD. Okay, you can make U and V orthogonal, but then, okay, you lose because now sigma is not, it's not invertible, it's not even square. So these have, I mean, they're not conceptually very different. They're just, sometimes it's useful to have U and V be full orthogonal matrices. Question, do you use Gram-Schmidt to extend your basis? Yes, here this is Gram-Schmidt.
After all, we need a systematic way, correct?
Yeah, you need a systematic way, so you use Gram-Schmidt. Okay. So that's truncated and full SVD. What I want to do, okay, and what's the other advantage of full SVD? So full SVD answers the question that I began in the last lecture. Namely, it gives you a basis of Rm and a basis of Rn such that the matrix of A is sort of diagonal, right? So what does this imply? This implies that when you do the full SVD, then the matrix of A with respect to B and C is sigma for B equal to the VIs and C equal to the U's. Okay. So this is the one new interpretation you get out of the full SVD that you don't get out of the truncated one. If you really want a input basis of RM and I'm sorry, input basis of Rn and output basis of Rm, such that the matrix of A in those bases is close to diagonal, you do the full SVD. So this was our original question. Okay, so what I want to now point out, so the SVD, it's kind of a pain to compute, right? You need to form A transpose A, then you need to diagonalize it, you need to find its eigenvalues and eigenvectors, then you need to multiply them by A, and then you get this SVD. But once you get the SVD, you can do everything. You can do everything in the course. Okay, so some people call this the Swiss Army knife of linear algebra. So let me now tell you why that is the case. Why is well, the reason is because it has the following connections, the concepts that we've studied elsewhere in the course. So the most obvious one is that the rank of A is the number of non-zero singular values. Okay. The way I defined it, the singular values are always positive. But if you're doing the full SVD, you could think of the extra zeros as being zero singular values. So in particular, it tells you the rank. Okay, fine. Second thing is the second thing is once you have the singular value decomposition, so let's say A is equal to U sigma B transpose, and let's say this is a truncated SVD, then you can immediately read off the projection row space and column. Right? So U transpose is the projection onto the column space of A, and V transpose is the projection to the row space. Right? This is just follows from the fact that the non-zero right singular vectors are orthonormal basis for the row space, and the non-zero left singular vectors are an orthonormal basis for the column space. So you can read off all these projections once you have the SVD. A third thing, which is maybe less obvious, is you can also just solve least squares problems. You can solve least squares problems almost trivially. So to solve AX equals B, or to solve the okay, to find least squares solution. So maybe I'll write it that way. Well, what can you do? So first, you have this SVD of A here. You're going to use that somehow, right? Well, I'm going to form a new matrix, A plus, which kind of looks like the SVD, but I'm just going to invert all the singular values. So I'm going to use the SVD to make a right inverse of the matrix. Okay? So rectangular matrices don't have inverses, okay? But they do have these things called a pseudo inverse. So what am I going to do? I'm going to form a matrix A plus, which is going to be V sigma inverse U transpose. Okay, so this is called the right pseudo inverse. And this is really easy, right? Why? Because sigma is diagonal. It's really easy to make sigma inverse, right? So sigma inverse is just this matrix 1 over sigma 1 up to 1 over sigma A. And those are all, the inverse exists because they're not zero. That's why I use the truncated SVD. So form this matrix. Okay. And now, here's the cute observation. Suppose you consider, suppose you look at the vector x hat equals a pseudo inverse b. Okay. So just that's what you would do if really it was an inverse, right? You would just hit b with the inverse. But now let's see what happens when you hit b with the pseudo inverse. Well, what does this satisfy? Well, ax hat equals a pseudo inverse b. That's the definition, right? Now what is that? So a is u sigma v transpose. A pseudo inverse is v sigma inverse u transpose v, right? Aha, but v transpose v is the identity of size k because v has orthonormal columns. So this is u sigma inverse u transpose v. Aha, this is also the identity. So this is u transpose v. But u transpose is the projection on the column space, right? So that means that this x hat that I constructed very easily given the SVD, this satisfies ax hat equals the projection onto the column space of B, which means it's a least squares solution. Okay, so once you have the SVD, not only can you find the rank, find the projections on the row and column space, you can also solve least squares, which in particular means you can solve linear systems. So this is kind of cool. It gives you a way to solve linear systems without row reduction. Okay, there's a different way to solve linear systems. So any questions about that point?
Just to rewind, I believe that why is the SVD Swiss Army knife part, the first statement, I believe that is because the null space of A transpose A is the same as null. Well, no, not that. Not scratch that. The null space doesn't exactly have to be the same, but the dimension of the null space of A transpose. Well, is it? Yeah, okay.
Well, so you can prove item one in many different ways, but really it just follows from the main SVD equation, which is this. Right?
Yes.
It shows, I mean, it shows that there is a basis for the row space of k vectors. That means the rank is k. So, I mean, maybe you're thinking about how we derived the SVD in the first place, how we derived that fact. That's correct. That has to do with the fact that the null space of A transpose A is a null
Yes.
space.
Yeah, the null space can be the same because the dimension.
But the point I'm trying to make is once you have this SVD, you can just read off all these other things. Okay. What is A plus? Question. A plus is the pseudo inverse. It's a new notation. Okay. Okay. It's a new thing. We're not going to develop it further in the course, but it is an important thing that comes up a lot.
I'm sure that a lot of us like seeing that.
A plus. Oh yeah, good. Yeah. So, yeah. So okay. In quantum mechanics, it's also there are many notations. It's also called some people call it a dagger, but it's confusing because dagger really should mean something else. But anyway. Okay. One question: is this faster?
Oh, sorry.
Sorry. What were you saying?
I was just wondering if there was an easier way to visualize a pseudo inverse because I see the formula next to it and that makes sense. But like, is it like 1 over A or what's a good way to think about it?
Yeah, 1 over A is a good way to think about it. The pseudo inverse. Yeah, I mean, okay. So here, let me just draw. Okay, so here's another way to think about what the pseudo inverse means. I won't prove this. Okay, so the pseudo inverse is the inverse of the so what you can do is okay, so let's suppose you have this linear transformation from the row space of A, the column space of A, by A of X, right? Remember this from 2 lectures ago? Okay. So then the pseudo inverse is actually the following. The pseudo inverse is the projection onto the column space of A, followed by D inverse. Okay, so that's what it, so the point is A is not invertible, but if you now take something in, I guess Rm and project it onto the column space, then this T is an isomorphism, right? So the pseudo inverse is applying the isomorphism after projecting on the column space. Now I haven't specified exactly what basis this is happening in, so this is, you'll have to, I mean, I don't want to prove this because I don't want to spend more time on it, but you can think about that. Does that help? It's the inverse restricted to the column space. That's one way of thinking. Okay, but okay, and finally, I want to make one last remark. Is that if the matrix is symmetric, then the SVD is the same as the spectral decomposition. Well, then, okay, then, so maybe then this is equal to some PDP transpose, right, by the spectral theorem. Then the SVD is the same, right? Then U is equal to P, V is equal to P, sigma is equal to D. Okay, so what's the proof of this? Well, if A transpose equals A, then A transpose A is just A squared, and that has the same spectral decomposition with a D squared, right? You just square the eigenvalues. So then this implies that the singular values, or I'm sorry, there's one change. The singular values are the square root of lambda I squared, which is the absolute value of the I. So sigma is the absolute value of every entry of D. Okay, so if the matrix, so SVD works for any matrix, rectangular or whatever, but if the matrix is symmetric, then it gives you the same thing as the spectral theorem, but with absolute value signs in front of the eigen. Okay, so that's another connection. But in general, it can be very different from diagonalization. It's not the same thing as diagonalization. So so why is this not the same thing as diagonalization? What's the essential difference between SVD and diagonalization? I mean, there are many differences. SVD works for rectangular matrices. But okay, so for square matrices, SVD gives a pair of bases such that this is diagonal. Okay, and this is a problem because then you can't do things like, you can't take powers, right? Because if the B and C are not equal, it doesn't make sense. But diagonalization gives one basis. Okay, so diagonalization is a more a stronger thing than taking SVD, but SVD you can always do, and it has other good properties. I mean, okay, SVD always gives orthonormal bases. Diagonalization does not. Okay, you should think about the relation between them. Okay, so I want to end with a cool application of SVD. And the application is to image compression. Okay, so let me show you an image. So here's an image of a tiger, which I guess maybe is on many people's mind because of Netflix. And now I want to, so this is an image, and let's say I want to compress this image. I want to store this efficiently. In fact, that's what happens with JPEG or any of these image formats. So so now this tiger was actually a 500 by 800 pixel image. So if you figure that out, that takes about 1 megabyte of storage if you really want to store all the pixels. So I want to store something that looks like a tiger, but using fewer pixels. So of course, I'm going to turn it into a matrix. And the entries are going to be the grayscale values. That was a color image, but let's make it grayscale. So it's some number that shows how white or black it is. So now I have a matrix. Now I'm going to take the SVD of that matrix. And so how many terms are there going to be in this SVD at most? Anybody have an upper bound? I mean, like truncated SVD. How many terms in the sum?
Okay, so first let's take a look. So A is a 500 by 800 matrix, correct? So the transpose of A is going to be 800 by 500. So then A transpose times A is going to be 800 by 800. So we should expect to have at most 800 eigenvalue.
Correct. At most 800 terms. Actually, the number of terms is the rank, and it's 500 by 800, so the rank is actually at most 500, right? Because the row rank is at most 500. So you can actually improve this to 500, but you're right. So let's take the SVD. Okay, so somebody did that on the internet. So let me show you what they got. So this is a plot of the singular values of the tiger, 500 of them, on a log scale. Okay. So log scale means, okay, I took the log base 10. So that means that if you're smaller they're sorted in descending order. And what I'm seeing is that the singular values are decaying very rapidly. Okay, so there are a few really big ones that are about like 10 to the 2.5. But then, they actually go down pretty fast. So, I mean, for example, 10 to the 2.5 is, I don't know, it's well over 100. It's 300 or 400. So this, the first few singular values are over 100 times as big as, let's say, the 100th singular value. So what I can do here, and here's the idea behind the image compression, is I can throw away all the singular values after some threshold, let's say 50. Okay, so I'm just going to make some arbitrary threshold for now, let's say 50. I'm going to just throw away all the other singular values. So what happens when I do that? Well, So the next step is the next step is going to be only keep the top singular values. Let's just say keep 50 of them. So I'm going to make a matrix A tilde, which is just going to have 50 of these terms instead of 500. That's where the compression happens. Right? I'm going to have summation I less than 50. I just throw away the rest. And by top, I mean the largest one. Right? They're sorted. Now, how much space does this take? Well, there are 50 terms. Each term, I have to store 2 vectors, right? UI and VI. And each vector actually only takes roughly the number of entries. So it takes 500 plus 800 space, right? Because this is the key. Each term is, I don't need to store all the entries. I just store the 2 vectors. So the total space for this is this, which if you work it out is about 100 kilobytes, maybe like 65 kilobytes or something. Okay. So by throwing away all with the small singular values, this is where you got the compression. And now let's see what the results are. Okay. So these are the results. So there's a full rank tiger, rank 500. Rank 200 tiger looks pretty much the same. Rank 100 tiger also looks pretty much the same. Rank 50 tiger, you can see a little bit of degeneration, but it's not so bad, right? It's still pretty much to the human eye looks the same. Rank 30, you can really tell things are getting worse. Rank 20, it still looks like a tiger, by the way. Rank 10 tiger, okay, rank 3 tiger is just, you can't tell what it is, right? But even up down to rank 10, you can tell what it is. So this is, I mean, this is actually somehow the main, one of the main techniques in image compression, and probably the main way JPEG, for example, saves data, saves space. You take the SVD and just throw away the small singular values.
Professor?
Yep.
I wonder what is the order of growth of the algorithm for the image compression?
Yeah, so it's a good question, which I'll send an article about it. So how long does it, how fast is the algorithm for SVD? I mean, okay, I can give you a rough answer. Roughly the answer is order, if you want rank K, it's order K n to the, it's order KMN squared or something like that. That's n upper bound, you can do better, but okay, we can discuss more offline. Yeah. It's an active research area. Okay, so that's what I want to say about SVD. And that is the end of the linear algebra portion of the course. And yeah, I mean, maybe we'll just pause for a moment and maybe look at this picture, which, you know, maybe now you understand why I showed you this picture at the beginning, that it's this multifaceted thing where we had, you know, we had linear equations, we had row reduction, we had eigenvalues, diagonalization, like orthogonal projections and SVD, but they're all connected in this very sort of nice way. And by passing between these different, you know, methods of decomposing matrices and vectors, I mean, you have lots of really stunning applications to different areas. Okay. Okay, so now there was a question, how did we get 500 plus 800? Okay, let's go back there. How do we get 500 plus 800? Well, there are 50 terms in this sum over here. For each term, you need to store one number, the singular value. I'm just counting that. Okay, so it's really plus 1. But now to store the U V transpose, the point is you don't need to write the whole matrix. You just store U and V. U is a vector which has 500 entries, and V is a vector that has 800 entries. So that's 500 plus 800. Does that answer the question? Okay. So now I'm going to briefly introduce the second part of the course. What is the conceptual meaning of singular values? Okay. Okay. In that example, well, I'm just going to give a heuristic answer. So, yeah, you can prove a theorem to the effect that keeping the top singular values gets you some sort of good approximation to the matrix. Conceptual meaning is okay. So I'm just for images, the conceptual meaning is yeah, what is the conceptual meaning? Okay, sigma I is a measure a variation in independent directions. Actually, orthogonal direction. So okay, maybe that doesn't make much sense, or maybe another thing to say is that the large singular values contain the information. So if you have a signal, which is a physical concept, the singular values measure the energy of that signal in various directions. I don't know if that helps. Yeah, in that example, I mean, what's an easy way to say what it means? Well, okay, I'm just going to tell you a crazy theorem, which we won't prove. You can consider the vector space of m by n matrices. Okay. Then you can prove that if you take A tilde to be the sum of just the top R terms in the SVD, okay, this is the closest rank K matrix to A in the least squares norm. Okay, so we won't prove this, but staying to the top singular values is a way to find the closest low rank matrix. Does that answer the question? Won't prove this. So low rank means compressed, right? You can store low rank things using small amount of storage. And so the SVD is giving you a way to find the closest thing that can be stored with a small storage. Does that answer? Does that help? No? Yes? Okay. Okay. So now, okay, I guess I spent way more time on that than I needed to. Let's briefly talk about differential equations. Well, not so briefly, we have 35 minutes. So what's a differential equation? Well, it's something you did in Math 1B, I suppose. But what is it? This is an equation where the unknown is a function. Okay. So y of t, that's the notation we'll use. So that's a function from reals to reals, let's say. And the equation relates the function to its derivatives and maybe some other functions. And maybe other functions. Of this variable t. So for example, and the main kind of equation we'll study in this course, for example, here's an equation, 5y double prime minus 6y prime plus y. So these are all functions of t equals, I don't know, sine t. Okay, so that's an equation. The unknown is this y, and its derivatives also appear. And the main thing is this equals now means equality of functions. So it's an identity. Okay. So why would you care about such an equation? Well, I'll give you two applications, two common applications. So here's one application. So here's in some population growth models, here's a principle, which is the basis of the model. The rate of growth of population is proportional to the population. The more people there are, the faster it's going to grow. How do you model that mathematically? Well, let's define a function pop from reals to reals, maybe positive to reals. So pop of t is the population at time t. And now my equation turns into, if I were to write that in terms of math, well, the rate of growth of the population is the derivative, and that's proportional to the population. So it's some constant times the population, and that is a differential equation, right? So naturally, these kinds of rules lead to differential equations. And the kinds of questions you can ask are, well, one question is, what functions satisfy such an equation? That's one question, right? What are the all possible functions that could satisfy this? Suppose I know, suppose I know that local, so the key word here is local. So this describes what happens at every instant of time, right? The derivative at that instant is related to the value of that instant. What function satisfies such an equation? That means, can I find the whole function? I'm going to call that global. Can I actually write the whole function given this local information? And the other natural question, which is a prediction question, given the population at some time, let's see, say at time 0, what is the population at some other time t? Can I figure that out just knowing the equation? That's a very natural setup, and that actually, well, is used a lot in modeling population growth and other kinds of growth. Okay. A second application is comes up in physics a lot, is this picture, which probably many of you have seen in high school. Suppose I have a spring connected to a box sitting on some surface that has friction. And suppose I measure, it has some equilibrium position 0, and I let y of t be the position at time t. And so, if I pull this thing, and maybe it has some velocity, so y prime of t is velocity at time t, then how is this thing going to move? Well, I can model that mathematically, right? So high school physics, I have Newton's law, which says F equals ma. And what that means is that the net force is equal to the mass times the second derivative of the position. That's acceleration. Then, okay, what are the forces acting on it? So one is Hooke's law, which says that the spring has a restoring force that's proportional to the displacement. So F spring is equal to minus K, where this is a spring constant, times the displacement. And then I finally have the law of friction, where the amount of friction is going to be proportional to the velocity. So the faster it moves, the more friction. And again, it's going to go in the opposite direction of the velocity, so it's minus C y prime. If we combine these things, well, this is the net force, right? Then what do I get? I get that my double prime t equals minus K y t minus C y prime t, which is another differential equation, right? So this natural spring system just gives me a differential equation. This is like the basic problem of physics. So those are two instances where this comes up. And now what we're going to talk about is how to solve these, right? So we're not going to solve these in full generality. We're going to solve only first and second order equations, which means equations where derivatives appear with degree 1 and degree 2 for now. So start with simplest case. So what is the simplest case? Well, the simplest case is a homogeneous first order linear ODE. So this is a lot of jargon which you need to know to somehow navigate this area. Homogeneous means the right-hand side is 0. Okay. Homogeneous will become clear in a moment. Okay. First order means only one derivative. Linear means it's linear in the function y of t. ODE means only one variable. This is just a fancy way of saying an equation of type this: y prime t equals a y of t. Okay. And there are two questions I can ask here. So question 1, given such a differential equation, so let's call this equation star. Find all functions y of t, solving it. Yes, somebody raise their hand, please. You can ask a question.
Okay, so I wanted to ask, like, for example, if you have like if you have an equation that says like dq over dt is something, and dq over dx is something, that is called partial differential equation.
That's correct. If you have multiple variables and partial derivatives, that's called a partial differential equation. That's not ordinary differential equation. Correct. Okay, so that's the first question. The second question is, given the equation and some initial value, let's say you know the value at 0, find some specific y of t satisfying the initial condition. These are two different questions. This is called an initial value problem. And this is called find the general solution. Okay. So for this kind of equation, as far as I understand, you already did this in Math 1B. So let's answer the first question. Well, can anybody think of a solution to this ODE? So suppose I give you this equation star. Can anybody think of one solution?
Oh, it would be
E to the
well, it's
Yeah,
going
e
to be
the
one.
AT.
Well, e to the at. Okay.
So somebody. Or were you saying something else?
It would be, well, to be in general, y equals c e to the a t.
Great. So
Never forget the c.
never forget to see. Okay, so you can check if you take y of t equal to any multiple of an exponential with the same a in the exponent, that's important. Then y prime of t is equal to ac e to the at, which is a y t. That's a solution. Actually, these are all solutions. We won't do this here. I don't know, maybe you did it in Math 1B, but we won't do it here. Okay. So what that means is that the general solution is a set of all multiples of CE of e times e to the at. Okay. And just observe, by the way, this is a one-dimensional vector space, right? If it has 0, because you can take C0. If you add two things in here, then you can you get another solution, right? So it's a vector space. Okay. And what about the second answer? Well, let's just do the second answer with an example. So given y of 0 equals 1, find a specific solution. Well, how do I do that? Well, I just solve the equation, right? So I solve for c, right? C times e to the a0, that's y of 0 equals 1. That's just c equals 1. So the solution is y of t equals e to the at is a specific solution. And pictorially, what's going on here is the following. Let me draw a picture. Actually, maybe I'll erase this for now. So what's going on here pictorially? Well, there are many functions, right, that solve the equation. So they're all exponentials. So they're all e to the at times a constant. So you have this is like maybe half e to the at. This is maybe e to the at. This is e to the 2e to the at. This is 3e to the at. The general solution is asking you to find all of these. The particular solution is asking you at 0, suppose I know that y of 0 equals 1. There's only one of these that satisfies that, right? That's this one. And that is the solution to the initial value problem. Okay, good question. So the question is, how do we know that there are no other functions that satisfy the equation? I'm not going to tell you. That requires a proof. So I don't know if you prove that in Math 1B. It's not hard, but it's not really the focus of this course. It requires a proof. It's not obvious. Okay, so it's a proof which is a calculus proof, and since that's not really the focus of the section, I won't prove it. But you can maybe read the book or for some references. But it's a good question. Any other? Okay, so that's really all there is to say about linear first order ODE. The general solution is always an exponential. And to find a particular solution to an initial value problem, you just solve one equation, which is really easy, actually. I want to give a little linear algebra perspective on this question. I think it's particularly The linear algebra perspective is given such an equation, you can consider a vector space. The vector space of all functions from R to R that are infinitely differentiable, let's say. We want to be able to differentiate the function in order to, we don't want to have a function that you can't differentiate, right? Then, sorry, this is A. This equation, you can define a linear transformation D from F to F by D of Y is just the derivative. Okay. And now the differential equation is actually just an eigenvector equation. Okay, so right, it's asking for vectors such that applying the linear transformation doesn't change the direction. It's multiplied by constant. And so what we really proved is that the eigenvectors of differentiation are exponentials. What are the eigenvalues, by the way? Any thoughts? Is it A?
So that would be A.
Yeah, A is an eigenvalue, but which A could,
The initial
for which A
condition.
is this satisfiable? Right, so this is an eigenvalue. This is an eigenvector. So yeah, what A's could be eigenvalues? For which A does it have a solution? Somebody said everything in F. Okay, that's not quite right because eigenvalues are numbers. Somebody said A not equal to 0. Well, why can't 0 be an eigenvalue, right? There are functions whose derivative is 0, right? Namely constant functions. So 0 is an eigenvalue too. Somebody said A to the n for any n. Yeah, that's true. If a particular A is an eigenvalue, then so is A to the n for any n. But I'm actually asking a question. Okay, so maybe this is a little confusing. Here A was given, right? But now I'm asking here a more general question. Just consider the operation D. There's no A inside D. What are its eigenvalues? For which A does this equation have a solution? All real numbers, yeah. Okay, so this might look a little weird. We're used to only having a finite number of eigenvalues. This is a linear transformation that has infinitely many eigenvalues. There's no problem because it's a linear transformation on an infinite dimensional space. Okay, I thought that was very cool the first time I learned this, that exponentials are the eigenvectors of differentiation. That's one way to define exponential. Okay. So now I want to move on to second order. And second order just means equations of this form, a y double prime b, sorry, plus by prime b plus cy of b equals 0. Call this double star. And the homogeneous actually refers to the 0 on the right-hand side. So there's no other function on the right-hand side. Second order refers to the y double prime. This was the type of equation that appeared in the spring system. And again, you have the same two questions. First question, given an equation, find all y of t. This is the general solution. Second question, given the equation and some initial data. So y of 0 equals some capital Y naught, y prime of 0 equals capital Y1. Find a specific y of t. Okay, now, by the way, in the spring system, this is the initial position, and this is the initial velocity. So the second question is very well motivated from physical point of view. It's asking, if I know the position and velocity at one moment in time, can I predict what it is at some other time? And is that unique? Okay, so I'm going to show you these via an example. Let's look at the following equation. Y double prime minus 3y prime minus 4y equals 0. That's a second order homogeneous linear ODE. I've omitted the t's. They're all functions of t. I just didn't write t because it's understood from the context. So let's turn this into a linear algebra problem. Okay. Well, so again, define this vector space of functions. And now define a linear transformation. So I'm going to do this a little differently. The previous one I talked about an eigenvector problem. Now I'm going to set this up as a linear, just a linear system of a linear system, or the equivalent analog of a linear system. And now define the following linear transformation. T of y equals the second derivative of y minus thrice the first derivative of y minus 4y. So I'm going to define this linear transformation. You have to check that it's linear, but at this point, we've done this many times. So now when I define this, well, this equation is literally the equation T of y equals 0. Right? I'm just looking for the functions y, which are vectors in f, which get mapped to 0 by this linear transformation. So this is kind of cool. What this means is the general solution is just the kernel of this linear transformation T. So let that sink in for a moment. This is like AX equals 0. But instead of A, you have this other linear transformation T, which is not a matrix, and which is acting on this infinite dimensional vector space. So that's nice because, okay, it's just a system of linear equations. How hard can that be? What's not nice is, well, you can't use row reduction. Why can't, do you think we should try to use the correspondence principle here? Could we turn this into a question about Rn? Who thinks we can, anybody think we can turn this into a question about Rn? No, why not? It's infinite dimensional, exactly. F has infinite dimensional, so no basis. Okay, so we need some other way. So I'm going to show you a cool way to do this. Actually, a way that reduces it to the degree one case. Here's the idea. Use algebra of linear operators to reduce to first order. So what do I, by the way, linear operator is just a linear transformation from a vector space to itself. It's a fancy word for, it's the analog of a square matrix. It's a linear transformation from a vector space to itself. And what do I mean by algebra? That's a bit more interesting. By algebra, I mean that, well, if you have two linear operators, so given two of these things, you can actually, you can add them, you can scale or multiply them. Well, you can add them. So what does that mean? Literally, it means it's the linear transformation that just, adds the two outcomes. You can scale or multiply them. Or this is add, scale or multiply. But you can also actually just multiply them. What does multiplying mean? I'm actually defining, maybe I should say define the following. Well, it's just composition. So really, this is just like matrix algebra. Right? You're used to things like squaring matrices, adding them, etc. You can actually just do that to linear transformation to operators. Right? It's important that they're operators. Otherwise, when you take composition, you may not get something of the right type. And finally, there's an important linear transformation identity, which plays the role of 1. Okay. So now you can kind of do algebra with these linear transformations, even though they're on an infinite dimensional space. This is actually a really powerful idea. But any questions about what this means? Okay. So let me apply this in our setting. So our example is this particular equation, right? And I'm interested in finding the kernel of this T. So I have T, which equals, I'm going to write it in a funny way. I'm going to write it as D squared minus, I forget, was it a 3 or 4? 3. 3D minus 4I. Where D is a differentiation operator. This makes sense. I define what it means to add square linear operators. And indeed, that's what this is doing, right? If you look at the definition in the bottom right corner here, you differentiate twice, and you subtract the derivative, and you subtract the function. That's the same as doing this. Any questions about that point? It's quite an abstract point. So, and historically, it's been a source of confusion. So if you have questions, feel free. I mean, you should always feel free, but.
Why are you subtracting for identity?
Yeah, so the reason is, I look at, look at the definition. here of my linear transformation. So what does this do to a vector? Well, it differentiates it twice, then subtracts twice the derivative, then subtracts the vector itself, aka the function, right? That's why I have -4 identity. Does that make sense?
Got it.
Yeah. Okay. So this is a quadratic polynomial in D. So now I'm going to do something that looks a little crazy. I'm going to imagine that the D is a linear operator on an infinite dimensional space. I'm just going to imagine, well, what would happen if this thing was a variable? So I'm going to now introduce a new variable R. So it's something I'm going to call the auxiliary polynomial.
I have a question.
Yep.
Why are there no i's in front of the d squared and the -3d?
Because D itself is a linear transformation. So D times I is just D.
Okay.
So okay, maybe this will become clear if I run this on an example. So the reason I need a 4i is that t of y should be d squared of y minus 3d of y plus 4i of y. I need something here because remember the type of t is that it's a linear transformation, right? I can't just put a number there. That's not a linear transformation from f to f. Does that make sense? Like if I didn't have the I here, then t cannot be equal to some linear transformations minus a number.
Right.
Just does that make sense?
Yeah. Thank you.
Okay, so I'm going to construct a polynomial r squared minus 3r minus 4, and you literally just turn all the d's into a new variable r. Okay. But now I'm back in high school, right? I have a polynomial. I have a quadratic polynomial. I can factor it. Let's factor this. If you factor this, you get that this is r minus 4 times r plus 1. Use the quadratic formula or whatever. Right? Now the punchline is that the same factorization works for the operator. Now, why does that work? Why does it make sense? Well, let's just check. You have d minus 4i times d plus I. What does it mean? Well, it means d composed with d plus d composed with I minus 4i composed with d minus 4i composed with I. If you go back to the previous page, right? If you go to the definition of what algebra for operators means. That's the definition. Well, what is that? This is d squared. Now here you have d of I and I of d. But there's something special here. In general, AB is not BA, right? But if one of them is I, then it is true, right? So this equals d of I. So you actually get that this is plus, which then equals d. So this is plus, or I guess minus 3d minus 4i, which is d. So we're happy. That's a pretty creepy smiley, but yeah. Okay. Okay, so what's the upshot of this? So the upshot is that each of these parts individually is a first order ODE. So let's solve I don't know, d minus 4i. let's call it y1 equals 0, then well, okay, so d minus, consider this first order ODE. We already figured it out. General solution is e to the 4t times c1. And the key point is, if you have such a solution, then what's t of y1? Well, it's, so I factorized t above, right, in this manner here. But again, yeah, all this rests on the fact that differentiation is a linear transformation. I could have written it the other way too, right? The order doesn't matter because the only operators appearing here are d and I. So actually, I would get that this is d plus I times d minus 4i times y1. But this thing is 0. So this must be 0. So that means all of these must be solutions of t of y1 equals 0. Any questions about that?
I want to ask why you can switch the order of d plus I, d minus 4i.
Yeah, why can you switch the order? The reason is that the reason is that they commute. So the reason is that if you're, well, let me answer the question over here. Very important question. Well, the answer is, by the algebra rules, you can expand both of these, right? This is d squared minus 4 d of I plus I of d minus 4 I of I. And this is d squared minus d of I minus 4 I of d minus 4 I of I, right? The key is that these these two terms are equal, okay? And these two terms are equal. And the key reason is d of I equals I of d. Identity commutes with everything. Does that answer your question?
Yeah.
It's a good question because you can't do this in general, right? I spent so much time during the linear algebra portion telling you that you cannot do this in general, but sometimes you can. And one of those times is when one of the operators is the identity. Okay, so once you do this, the point is you get for free that all of the solutions of just one of the factors, namely this, must be also a solution of the big equation. Similarly, d plus I y2 equals 0 has general solution c2 e to the minus t, where c2 is an r. And then all of these must satisfy t of y2. Now I'm going to write it in the other order. t minus 4i, t plus I y2 equals 0. So that's kind of great, right? By just doing first order ODE, I was able to get two subspaces of solutions to my second order ODE. So what's the conclusion? Both of these both of these sets are solutions of t of y equals 0. And actually, because the kernel is a subspace, their sums must also be a solution. So you actually get that the span. So you actually get that this entire set C1e for t plus C2e are solutions. This is equal to the span of e to the 4t, e to the minus t. So to summarize, this span is contained in the kernel. Okay, somebody asked a very good question. Are they the only solutions? Again, the answer is yes, but the proof of that is beyond the scope of this course. It's actually not that easy to prove that. Maybe you can prove that after taking Math 104. So in fact, these are the only solutions. Will not. So actually, we found the general solution. So this is an important point. But what's the summary? How did you obtain 4 and minus 1 for the values again? Well, you obtain 4 and minus 1 by solving these two boxed ODEs. And these are first order ODEs. So we go back to our here, homogeneous linear ODE of first order. And I'm just going to write this as, this is another way of writing this equation is this is D minus A times identity of Y equals 0. Does that make sense? Because now, in our setup, we have here D minus 4i, so you get e to the 4t. Another question is span exponentials is equal to kernel of t. Yes, I was going to write that next. Conclusion. Kernel of t is equal to the span of e to the 4t, e to the minus. And that's the general solution. What is the significance of choosing exponential? Well, we don't actually have a choice. Those are the only solutions. That's just for the first order ODE, you can do it using Math 1b or something. Exponentials are the only solution. And okay, I didn't tell you the proof here, right? But this proves that they're the only solution. What we did prove is that they are solutions, right? This algebra thing we did prove this fact, right? That the span of the exponentials is contained in the kernel. We didn't prove that's the only thing, but we did prove that it's contained. Okay, so that's how you find a general solution. So here's the summary. And here, given ay double prime plus by prime cy 0, suppose the auxiliary polynomial ar squared plus br plus c factors as a times r minus r1 times r minus r2 for distinct real roots. So in our case, those were 4 and minus 1. Then the kernel of t, where t is ad squared plus bd plus c identity, is equal to the span of exponentials with these exponents. Okay, so I'll end there, and next time we'll do the initial value problem and what if roots of auxiliary polynomial are not real and distinct. Okay, really sorry for going so over time. The SVD thing I was hoping to spend much time on, but